In this example, we're finding where f of x equals 1 over x minus 2 is concave upward and downward. Remember, whenever you're finding where a function is increasing and decreasing, you need to use your first derivative and separate it with your partition numbers. Whenever you're deciding where a function is concave upward and downward, you need to use your second derivative and separate it with partition numbers. So we need to take this 1 over x minus 2 and find its derivative and then its second derivative. So if we don't want to use the quotient rule, which generally takes the longest out of all our derivative rules, then we want to change this into something that we can find the derivative of more easily. So I'm going to rewrite our function f of x, but I'm going to change this from a fraction to just bringing this denominator up to the top with a negative exponent. Remember, whenever you move something from the numerator to the denominator or the denominator to the numerator, you just add a negative on its exponent and it's the same problem. So f of x equals 1 over x minus 2 is the same thing as the quantity of x minus 2 all to the negative first power. Our exponent in this case was just a 1 since we didn't have any. So we get x minus 2 to the negative first. And now when we want to find the derivative of this, we can just use the general power rule, which says we're going to take this exponent and multiply it out front. We'll then subtract 1 from the exponent, but then we have to take what's inside the parentheses and multiply its derivative out front. So x minus 2's derivative is just 1, so we're multiplying this entire thing by 1. We're going to get exactly what we had before. So we get f prime of x is equal to negative 1 times the quantity of x minus 2 to the negative second, all times 1, which means it's just going to stay the same. Now we need to find the derivative again. That's our second derivative. So we go through the same process. We'll multiply the negative 2 out front. We'll subtract 1 from it. And then we'll multiply the outside by the derivative of what's in the parentheses again, which again, the derivative of x minus 2 is just 1. So that leaves us with negative 1 times negative 2 is positive 2 times the quantity of x minus 2 to the negative third. And again, this times 1 has no effect. So we end up getting our second derivative is 2 over the quantity of x minus 2 to the positive third power. We needed to rewrite this simplified. We needed to change the negative exponent to a positive 1. And now that we have our second derivative, remember partition numbers come from when you set the top of your fraction equal to 0 or the bottom of your fraction equal to 0. This tells us where it's equal to 0 or does not exist, and those are the only values at which you could have a partition number. So the top in this case is just 2. 2 can never equal 0, so we don't even have to worry about that. But the bottom, x minus 2 to the third power equals 0, that can equal 0. And the way that we would find that is just by taking the cube root of each side to get x minus 2 is equal to just 0 again. And if we add 2 to each side, we'll get our x by itself which gives us x equals 2, and that is our partition number of the second derivative. So when we're testing concavity, we want to make a table or a number line, and we're going to test around that partition number. So we have x and f double prime of x. We're going to plug in our 2 for our x and a number to the left and right of it. So we'll test a number that's less than 2, which is just 1, and a number greater than 2, which is 3. We said that when we plug 2 in to the second derivative, that's when the denominator is equal to 0, which means the second derivative is undefined. So, when we plug 1 into our second derivative, we'll get 2 over the quantity of 1 minus 2 to the third power, which gives us 2 over negative 1 to the third. Negative 1 to the third is just negative 1. So 2 divided by negative 1 is negative 2. Please remember, you do not have to go through this entire process. As soon as you show this value here, you can just plug it into your calculator and get the negative 2. And all we care about from this is that it is negative. It's less than 0. So we'll make a note of that. All values to the left of x equals 2 will have a negative second derivative. That's what being a partition number is all about. Every number to the left of it will have a negative second derivative. Now we'll test 3. So we plug 3 into our second derivative, which gives us 3 minus 2 to the third. And we'll go through this one a little quicker. We get 2 over 1 cubed. 1 cubed is just 1. So we get 2 over 1, or positive 2. And again, all we care about is the fact that that is greater than 0, that it's positive. And we now know all that we need to know to decide where our original function f is concave upward and downward. So we say f is concave up on the interval. And now think about this. We want where the second derivative is positive. That tells us where it's concave up. So it's positive immediately to the right of x equals 2. So that means we'll say the interval 2 to infinity, but we put this parenthesis with our 2 to say that 2 is not included, but every number right after 2 is. So for instance, 2.1, 2.01, and so on. We then say that f is concave down on the interval, and now we want where our second derivative was negative. That tells us where it's concave down. So every number to the left of this x equals 2. So that means we'll start with our lowest number possible, which is negative infinity, and work all the way up to positive 2. But again, we do not include the 2. So f is concave up on 2 to infinity, and it is concave down on negative infinity to 2.